Great. So thank you. And indeed, I'm going to talk here about mostly a joint work with Yannick Viosa, as I'll introduce in a little while. So by way of motivation, though, I'm going to start with the previous project. This was a collaboration with Daniel Fisher's lab in Montpellier. And in this case, in their cell biology lab, they focused on a cell line of human colorectal tumor cells. And by keeping these cells under drug pressure for a long time, they generated a line that was irreversibly resistant to an investigational drug. And this particular drug is one that interferes with the cell cycle. So it was able to arrest cell growth at low doses. And what they did is they, as you've seen in some other presentations, they mixed these two populations, the sensitive and the resistant cells, together. And in this case, they grew them not only in two-dimensional plates, but also in tumor spheroids, which recapitulate some of the structure and the conditions of solid tumors. And what they found is that even when these resistant cells had been kept under drug pressure for many months, they still proliferated slower than the wild-type cells. So here you see a growth curve for the wild-type cells in blue, and the resistant cells with and without the drug in red. So these cells grow pretty much the same with or without the drug. But if you put the same drug dose on the wild type, then it very quickly dies, as you see in the orange there. And this fitness cost applied both in monolayer culture, as you see on the left, and when they put these cells and grew tumors in nude mice, as you see on the right. And this fitness cost was not frequency dependent. This was just a cost of the resistant phenotype on growth rate. Something else we know about tumor spheroids, because they've been very well studied, is that only cells that are close to the boundary of the spheroid are able to divide. And so when I built a computational model of this system, I accounted for this this contact inhibition and this competition for space by allowing cells to budge each other out of the way in order to proliferate, but only if they were close to the boundary of the tumor. And so what I did is I created an agent-based model that incorporated 4 different processes that we knew were going on within the real tumor spheroid. So firstly, in the top left, we have the cost of resistance, as I've just told you. Top right, we have the distance from the periphery. And those 2 factors affect the cell proliferation rate. Thirdly, we have hypoxia, which has been very well studied in tumors and tumor spheroids, that oxygen has to diffuse through the tumor spheroid and it doesn't diffuse very far. And the cells that have the least oxygen die, we get necrosis. And finally, the drug effect, which we were able to parameterize. And essentially, the drug had an almost linear effect on the proliferation rate, down to about, well, when the dose was increased until about 20 micromolar, and above that, it started to kill the cells as well. So when we put all of this together into a computational model, I obtained the results shown on the left. At the bottom there are the averages for many growth curves. The solid lines are medians and the dashed lines are means at the different doses. And the red line there is a control. The blue lines are very low doses, essentially too low to control the tumor. The orange line is the very high dose that kills the sensitive cells but allows the resistant cells to escape. And the dose 20 is this intermediate dose that was able to arrest tumor growth. And you see on the left that dose 20 is generally optimal. And on the right, we see that the actual tumor spheroids followed the same pattern. And at first you might think, well, maybe I fiddled it to fit the data, but actually this is a not very surprising agreement because we are able to parameterize the model so well from experimental data that basically the model had all the factors in it that were going on within this very well-controlled experimental system. But you also notice that there's quite a lot of variation in this dose 20. The mean is a lot higher than the median because in some cases the resistance does escape. And when I looked at that in the simulations, what I found is that the location of the cells really matters, the location of the resistant cells. So on the y-axis here is the proportion of simulations that had more than 10% resistance at day 28. So the initial frequency of resistance was only 1%. So this means that the treatment's failing. And if we put in the experimentally derived parameters, as I showed you, then the cells that were very close to the boundary of the tumor spheroid, they had these tumors had a very large, very high chance of resistance escaping. But so long as the resistant cells were initially at least a couple of cell diameters away from the boundary, then almost always the resistance was suppressed at this dose 20. Now, if I removed the fitness cost of resistance in the simulation, interestingly, the results didn't change very much. So they're a little bit worse, but they're not much worse. If I remove the growth period, so if I didn't allow the tumor spheroids to grow a bit before we applied the treatment, then the results suddenly get a lot worse. So in our experiment and in the model, we initially randomly mixed these two cell lines together, and then we allowed the tumor spheroid to grow for a bit before it was treated. And that seems to be an important factor here. And finally, if I removed this crowding inhibition completely, then the results suddenly become terrible. So what this conveys is that perhaps the most important thing going on here is this competition between cells that arises from the spatial structure, and not so much the fitness cost of resistance. So shortly after this paper was published, I attended a workshop that in a way is a precursor to this one, which was held in Leiden at the Lorentz Center. And this workshop, the theme was understanding cancer through evolutionary gain theory, and several speakers there discussed adaptive therapy. And one in particular who I'd never met before was Yannick Viosa. And Yannick was speaking about a critique of his of existing adaptive therapy models. And I got chatting with Yannick, and we decided to start collaborating together. And this project, as I say, it started off as a critique of some existing models, but it quickly matured into something more constructive, where we started looking at, well, what makes a good model and what assumptions must underlie a model for this to work? How can we generalize all these particular models that people have come up with, including myself and very many other people? So what we did, we settled on the most general model we could think of, the simplest model we could think of that's interesting. So here we just have two types. You have sensitive cells, which are denoted S, and resistant cells R. And we have a growth rate for each of them. So the growth rates here are denoted G. And we have some growth function GS, which is the growth rate of the sensitive cells. And we allow this to depend on any conceivable way, essentially, subject to some limitations, on the sensitive cell population, S, on the resistant cell population, R, and on the drug dose, C, which can vary over time, of course. We assume that the resistant cell growth rate only depends on the subpopulation sizes. So in other words, these resistant cells are fully resistant to treatment. This is a simplifying assumption. So the sensitive cells are sensitive to the drug, the resistant cells are entirely resistant. And we make two assumptions about these functions, GS and GR. So firstly, we assume that GS is non-increasing in C. In other words, the treatment cannot benefit the sensitive cells. And that's a straightforward assumption based on the fact that we assume that the drug here has some usefulness. And secondly, we assume that the growth rate of the resistant cells is non-increasing in S. In other words, the sensitive cells cannot benefit the resistant cells. Those are our two main assumptions. And we think these are reasonable assumptions, and they hold in pretty much all the adaptive therapy models that have been proposed. You'll note that we're omitting here a couple of things. So firstly, we're omitting any partial sensitivity of the resistant cells. And secondly, we're omitting any ongoing mutations between these two cell types. And I'll come back to that second assumption later on. And so what I'm going to present is a lot of mathematical results, most of which were attained by Yannick, who really led the technical mathematical parts of this study. And in the bottom right there, you see some of the papers that were important precursors for this work. So Martin et al., the work by Elsa Hansen, some of which she presented at this conference, and work by Cécile Carrère and colleagues, which looked at similar kind of ideas prior to us. So we're building on some very nice studies that were done previously. So what we examined was we examined 3 clinical outcomes. The first one we call time to progression, and this is simply the time for the tumor to exceed its initial size, which we're going to denote N0. We looked at what we call time to treatment failure, and this is the time until the tumor exceeds a maximum tolerable size. So this maximum tolerated size, N-tol, this is something that a clinician would have to set. The clinician would say, we do not permit the tumor to grow above this certain size, because above that size, it starts being dangerous, it starts overly affecting quality of life. And thirdly, we look at survival time, which is simply the time until the tumor reaches a lethal size. And this is obviously a clear endpoint. So what we formally prove is that if you start off with this very simple general model under those main assumptions that I've outlined, then these 2 results hold very generally in terms of prolonging survival. Under any of those 3 definitions of prolonging survival. So firstly, the optimal strategy is the one that maintains tumor burden as high as you possibly can, as long as sensitive cells remain. And we call this ideal containment. So we're calling it ideal because this treatment strategy is not constrained by any threshold on the dose that can be applied. So what the clinician would do in this case is keep applying a more or less constant dose, but then when the tumor burden starts to increase, despite this constant dose, they ramp up the dose. And towards the end, as the resistant cell population starts to approach the size of the sensitive cell population, the dose has to be ramped up a lot. And this is why it's called idealized, because in this idealized case, there's no restriction to how much that dose can be ramped up. And the worst option is to maximize the kill rate. In other words, to instantaneously kill off all of the sensitive cells. And we call this idealized maximum tolerated dose. And we look at these idealized solutions, as some people have previously, because they simplify the analysis and they give us nice insights that can also apply in non-idealized cases. So just to give you an idea of the mathematical intuition behind this result, what we see in the top here is a diagram. On the y-axis is the size of the tumor or of the subpopulations S and R. On the x-axis is time, so we're just looking at growth here. And suppose that our tumor initially has size N0, and at some later time point it has the resistant subpopulation has size R1 at time t. And we're going to denote the sensitive cell population by S1. Now, in this case, we're going to look at time to progression. So we're going to say the treatment is failing as soon as the tumor size exceeds this size N0. And therefore, R1 plus S1 must always be at or below N0. So suppose we start at our size R1 and we progress a very small time increment dt, then the resistant cell population during this time grows by an amount dr. And if we assume these are small, then the time for the resistant cell population to grow by this amount dr is approximately equal to dr divided by the growth rate, gr. So this is just like distance divided by speed. And under any treatment, as I just said, before progression, we must have S1 plus R1 less than N0. So in other words, S1 must be less than or equal to N0 minus R1. If we adapt our idealized containment strategy and we contain the tumor at initial size N0, then we get equality. So S1 exactly equals N0 minus R1. So by our assumption, that is the underlying assumption of this type of model, we assume that a larger S1 implies a smaller GR. In other words, the larger the sensitive population, the smaller the growth rate of the resistant cells. And this in turn implies that a larger sensitive population implies a larger time increment before the tumor before the resistant cell population grows by dr. So it follows that containment minimizes the growth of the resistant population, and hence it maximizes the time to progression. So I'm not sure that everyone will have followed the mathematics here, but what I want to emphasize is that this is relatively simple and intuitive, the reason why this works. And this, what we outline here is this is just an intuitive rough approximation of how these results are actually proved. Within the supplementary material of our paper, these results are proven much more rigorously using a variant of Cromwell's lemma, a comparison principle, which is based on more precise calculus than this. But what you'll note here is that we've not used any complicated tools from optimal control or any other heavy mathematical apparatus. So we've proven then that this ideal containment is optimal, but that doesn't necessarily tell you that the clinical gains are going to be very large. So what if we look at particular functions, growth functions? So for these functions GR and GS, we insert particular functions. One very common function that's used to model tumor growth is a Computational function, and that produces a density-dependent growth curve. But there are alternatives such as the logistic function, von Bertalanffy and others, which produce superficially similar growth curves. So on the left here, we see 3 untreated growth curves. Each of these has 2 free parameters. So what I did is I defined a Computational growth curve in black, and then I just tweaked the parameters of the other 2 functions so that they superficially resembled the Computational growth curve. Now, you can imagine that if you were trying to fit a curve to real data, you might say that any of these functions is an equally good candidate if you don't have very much data. But what you see on your right, on the right-hand side, is that the relative benefit of adaptive therapy or containment versus idealized MTD, this maximum tolerated dose, very much depends on which function you're assuming. So in the Computational case, we see a good benefit of containment versus MTD, even when resistance is relatively common. But if we look at a logistic function, then we see almost hardly any benefit, even for a superficially similar growth curve. And the von Bertalanffy and other functions, on the other hand, these functions describe stronger density-dependent competition between types, and therefore we see bigger gains from adaptive therapy or containment. So the message here is that the model really matters. All of these models predict that the containment strategy is better than maximum tolerated dose, but the size of the gain really depends on the extent of competition. So if you look at this Computational model in particular, we like this model because it's very well studied, because it seems plausible in the case of cancer growth, and also because it's been previously studied by Monroe and Gaffney, which gives us a good point of comparison. So here we have a carrying capacity K, and again, we have this drug dose C. These are our main parameters. And we have a lambda parameter here, but we usually set this to 1. So if we take that particular model, and indeed other models, we can obtain analytical results telling us exactly what are the times to progression and the time to treatment failure as we vary different parameters. And what you see here in these heat maps is that the initial frequency of resistance does matter, and so does the initial size of the tumor, N0. But the nature of this relationship really depends on what outcome you're looking at. If you're looking at time to treatment failure, then the key thing really is the initial frequency of resistance. So what matters here is, firstly, what is your outcome? You're looking at time to progression, time to treatment failure, overall survival, and also at what size are you containing the tumor? So we look at various different scenarios in the paper. So far I've just talked about idealized strategies where there's no constraint on the maximum dose that can be applied. But what we find is that that assumption doesn't matter very much. So in these graphs, what we've assumed, we have a parameter Cmax, which is simply the maximum dose that can be applied at any given time. And in the idealized case, which is represented by the dashed lines here, we just set that to infinity. There's no threshold. If we set that to 2, which in this case means that the maximum dose that can be applied is roughly twice what's required to contain the tumor, then we see the results are very similar. So here we see time to progression, time to treatment failure, survival time. Time to progression, you do slightly better in the idealized case. But if we're containing at the initial tumor size, then we find that in terms of time to treatment failure, survival time, there's almost no difference between the practical containment strategy and the idealized one. And also, if we look at intermittent strategies, so intermittent strategies compared to idealized strategies, our proof shows that they are always inferior to idealized containment. If we compare intermittent containment to the practical containment that has a threshold maximum dose, then we do see in some cases you can get subtle effects. So this is an example where all the dark lines, the dark black here is the overall tumor size in the case of intermittent treatment, and the blue and red in the dark colors are the sensitive and resistant cell populations. And if we're trying to contain an initial size here of 10 to the 10 tumor cells, then we can see that the intermittent therapy, this black line here, exceeds that threshold slightly later than the containment strategy, which is shown in gray. But the difference here is very small. And also, if we look at a slightly later time point, then the intermittent case quickly overtakes the containment case. So if one were looking for an optimal solution here, one might say, well, intermittent is better, but it's debatable whether this really matters in this simple model. So what about fitness cost of resistance? A lot of the theory behind adaptive therapy is focused on the phenotypic cost of resistance. This is something that's been emphasized in many reviews and many previous studies. However, as you'll see in our general model here, we have no cost of resistance. There's nowhere here that we've made any assumption about a cost of resistance. Indeed, we could have this function GR. It could, in the basic case, even exceed GS. So resistant cells could, in the baseline case, be growing faster than sensitive cells. You see, we don't make any assumption on this. And this is in common with previous studies, particularly this study by Martin et al. From 1992 that Yannick spoke about a couple of days ago, and the study by Monroe and Gaffney, which looked at the Gompertzian case. They didn't assume any cost of resistance. However, it is interesting to look at what are the consequences if fitness costs of resistance exist. So here is a model where we have something like a competitive model in which, instead of just having the overall population size on the denominator of this, this component here, instead of just having S plus R, we have S plus alpha R. In fact, in the examples I'm going to show you, I just set alpha to 1. So what we're really interested in is this parameter beta, which is the amount by which sensitive cells inhibit the growth of resistant cells relative to how much resistant cells inhibit each other. So we have this parameter R, beta, which is a competition parameter. We might also vary the baseline growth rates, rho S, rho R, which are shown here. And finally, we can vary the carrying capacities. We can have different carrying capacities to the resistant and sensitive cells. So you can see there are various different kinds of cost of resistance we might have. And if we look at two of those factors, so we look at this competition coefficient beta and the ratio of the two carrying capacities, we see, well, in the baseline case, both of these are equal to 1, and we get modest improvements from adaptive therapy versus MTD. But if we're able to increase both of these, and in particular, if we're able to increase this competition parameter, so that sensitive cells inhibit resistant cells more than resistant cells inhibit each other, then we can get better and better outcomes from adaptive therapy compared to MTD. And if these parameters are large enough, then we can even get infinite benefit. This means that the tumor can be controlled indefinitely. Another way of looking at that is looking at the final outcome of treatment. So in all the cases I've shown you so far, the tumor eventually reaches the lethal size and is lethal. But if we have these costs of resistance large enough, then we can have tolerable tumors. And at least we can have cases where it's tolerable in the adaptive therapy case. What about ongoing mutations? Well, I'm not going to go into this in detail, but suffice to say that if you assume that the initial frequency of resistance is consistent with the mutation rate, in other words, if you make the Luria-Delbruck assumption for how the initial frequency of resistance depends on the mutation rate, then we find that the effect on outcomes is really negligible, less than 1%, which is why we think we can neglect these. And finally, when might containment be suboptimal? Well, there are cases. So for example, if all of the cells are sufficiently sensitive to treatment, so if resistance means only weak resistance, then that violates our assumptions. This might not, and adaptive therapy or containment might fail. Secondly, if the sensitive cells don't inhibit the growth of resistant cells, because that would violate our other assumption. So you could have beneficial interactions or sustained exponential growth, that's less of it, absence of interaction. Thirdly, if the treatment induces mutations itself or induces plastic responses, as some people have already talked about, and as I think Eduardo Sontag will discuss tomorrow. And finally, there could be other costs of having a high tumor burden on the patient's quality of life or risk to their health. So in conclusion, we've shown that under some very broad assumptions, containment is optimal, even if we have no physical cost of resistance. But the clinical benefits crucially depend on how much competition there is. Practical treatment strategies can be close to optimal, so these idealized strategies are reasonable things to look at. But we can think of plausible scenarios where containment might fail, and I think the following speakers might go into that a bit more. So I'd just like to thank the people who worked with me on this project. The first paper I talked about is published, and the second one is in press. It should be out early in the new year, I hope. Thanks very much.
Okay, thank you, Rob. So we have many questions. So first question is from Hiteshi Mystery. So you assume that the death is dependent on critical volume, but empirically this is not the case. So what we know from 10,000 patients worth of data is that tumor burden is a time-dependent covariate in survival models. So that is your probability of surviving from one time interval to the next is conditional on the amount of tumor burden. So your conclusions would be reversed, would they not, if this known observation was accounted for? So that's this question.
Yeah, I mean, this is exactly the caveat that the last caveat in my previous slide, which is that if we assume that there are other costs of having a high tumor burden, that there's increased risk of, for example, metastasis or cachexia and so on, or that the tumor can, because it's large, it can continue to evolve more aggressive subclones, then our assumptions might be violated and MTD might be better. So this is true. And we do highlight this in the paper, and we are not trying to say that containment is always optimal. We're trying to clarify what are the assumptions you need for it to work, and what assumptions, if they're violated, might mean that it doesn't work so well.
Okay. So next question is from Renee Brady. So is the concept of ideal containment physiologically possible? While it's intuitive in theory, continuously ramping up therapy to contain the tumor burden may cause more harm than good in actual patients.
Yeah, so here's another slide. So the two cyan curves here, if you just focus on the two cyan curves, the dark cyan here is containment at the initial tumor size, where the maximum dose that can be applied is 1. So in other words, this is where you don't ramp up. And the paler cyan is where you do ramp up, and you have a maximum threshold of 2. So you can double your initial dose, but you can't do more than that. And what you see is that the one where you ramp it up, it delays progression, or it delays the point at which the tumor exceeds its initial size. But thereafter, the trajectories are much the same. So this ramping up actually isn't a very crucial component. The ramping up is something you do only when the resistant cells are very close to overtaking the sensitive cells. And that happens very late in the day. So there's only a small window during which you'd be ramping up the dose. And because it's only a small window, it really doesn't have that much effect on the results. So yeah, that's why we argue that these containment strategies can be practical. And indeed, constant dose can be almost as good as containment.
Okay. So the third question is from Velidi Vekil. So thank you for a very interesting talk. How did you find the optimal strategy? Have you implemented any optimization problem or computationally?
Yeah, so we didn't use any optimal control within this paper. So the mathematical intuition I sketched out earlier, which is a calculus technique, simply looking at these very small time intervals, this is an intuition of how we demonstrate that that idealized containment is the best option. So in the paper, we do three things. First, we've got these mathematical proofs of theorems showing what is optimal and what is not. Second, we've got a lot of analytical results where we look at particular functions and then obtain analytical results for the times to progression, times to treatment failure, and so on. And thirdly, we have a lot of numerical simulations where we demonstrate that our predictions are very close to reality and, well, very close to the numerical results. And also that if we violate some of the assumptions of that we made in our calculations, the numerical results stay close to the predictions. So we did all three, but we didn't do any optimal control.
Okay. So the next one is from Heiko and Ling. So very nice talk indeed. For early results on the ABM model, the calibrated model prediction very nicely agree with the biology. The ABM appears to be two-dimensional. The experimental spheroid are three-dimensional, yet the results are incredibly comparable. So does the spatial dimension not matter in this context?
I think if you had a three-dimensional tumor, firstly, if I'd simulated in 3D, then the initial population of the ABM would be larger, and therefore there would be higher probability that some of the resistant cells, you would have more initial resistant cells as well. And so there would be a higher probability that at least one of those would be close to the edge. And therefore the results might not have been quite so good had I run it in 3D. That's my expectation. But I think it was good enough to uncover the principles underlying this. So I think you'd find good qualitative agreement. I think maybe the quantitative agreement might be a bit closer because, as you saw, the median in the computational model was generally that we could contain the simulated tumor spheroid forever, whereas in reality, usually it did eventually, the resistance eventually did escape. So perhaps had we used a three-dimensional model, then we'd be a bit more accurate. That's my that's what I like to think would have happened, but I haven't tried it.
Okay, so we have two more questions. So one is from one of our attendees. So one of the risks of containment is that the growing tumor will produce novel mutations that will prove to be uncontainable. So what about more strict strategy where the tumor is held constant? And is the difference in treatment intensity that much different between stable and containment strategy?
But between the what and the containment strategy, sorry?
Between treatment intensity that much different between stable and containment strategies.
I'm not sure I fully understand the question. So our containment, yeah, sorry.
The question is about like effect of mutation. So that is not containable. So that
Yeah. So as I said, we looked at random mutations from sensitive to resistant, and we found that this makes very little difference. But it's easy to envisage other kinds of mutations. So, for example, plastic responses, which is something that Jill Gallagher and others have considered, which violates some of our assumptions, and then we might get more interesting results. And also, as I mentioned, that if treatment itself is mutagenic and increases the mutation rate, then we can get some other interesting results, which I think, as I said, Eduardo will speak about on Thursday. And another collaborator of mine, Timo Kuusinen, who's, I think, attending this conference, has also got a submitted paper on a similar problem. Okay.
So the next speaker is Fred Adler, the next speaker. The question is about how sensitive is the comparison of the three growth curve to the choice of carrying capacity K, in particular, how it compares with the various thresholds.
I'm sorry, how does it depend on the carrying capacity?
Yeah, those growth curve of the three growth curves to the choice of carrying capacity K.
Yeah, so the illustration there, which shows these three different models, we haven't looked in extreme detail comparing these in all cases, but within the supplementary material, we do provide analytical formulas for calculating the outcomes for those 3 different functions. And therefore, it's possible to use those formulas to simply plug in different values of k. But there's a huge amount in this paper, and so there's a limit to how many figures we could put in. But it's quite easy for a reader to do that, to just take the formulas and then plug in different values of k and see how the results vary.